This video is the first of two different ways of balancing redox reactions. So this is called the oxidation number method, and it is in a neutral solution, or in other words, non-acidic or non-basic. And all we're really going to do is just go through one example of this. Now in your notes you'll see that you have numbers 1 to 5a and 5b, and I'll label, those are basically the steps that we're going to go through as we go through this question, and I will label these steps as we go along, just in case you want to look back for reference. What do I do first, what do I do second, what do I do third, etc. So the first thing you want to do is assign oxidation numbers to all of the atoms in this chemical reaction. So if you go and do that, well, I do mine as well. We'll start here. So +1, -2, 0, -2, oops, +4, -2, and +1. Okay, now the next thing we want to do is we want to look at, have any atoms oxidation numbers change. So I just usually start the left hand side and I look at hydrogen, and hydrogen here is +1 as a reactant, +1 as a product, so it has not been involved in the transfer of electrons or the oxidation reduction aspects of this question. So I just go to the next one, sulfur, and I see sulfur is -2 as a reactant and +4 as a product. So all I'm going to do here is just draw an arrow going from sulfur to sulfur. Now what I want to write here is that, is this an oxidation or is this a reduction? So I notice that my number is going from -2 to +4. It's getting larger. So this is an oxidation. Now the other thing I want to write here is, for each sulfur atom, how many electrons did it lose? And we've gone from -2 to +4, which is a difference of 6. So we have had 6 electrons lost per S atom. And now we sort of look at the next one, and if we've got an oxidation, we need a reduction somewhere. So I've got oxygen, and it doesn't matter what oxygen you go to because they're both -2. I'm just going to go all the way over to here, like that. So this is going to be the reduction half of the redox reaction. And we also want to write down how many electrons per O atom did we gain. So the oxidation numbers are always for one atom in the compound, and we've gone from 0 to -2. So we have 2 electrons gained per O atom. Okay, so I'm going to go back and label now. So step 1 was to put oxidation numbers. Step 2, as you see up there, was to figure out how many electrons lost or gained per atom. So that's what we've just completed. There's step 2. Now step 3, and this is where people tend to make a mistake. In step 3, what we want to do here is figure out how many electrons are lost and gained per reactant. And that number might change because there might be more than one atom in the reactant. So we'll see how that works in this question. What I did here for the oxidation for sulfur was we just looked at one sulfur atom, and we saw that it lost 6 electrons right here. We were just focusing on the sulfur atom, but as in a reactant, how much did the reactant actually lose? Well, since there's only one sulfur atom in H2S, the reactant H2S also lost 6 electrons. So 6 electrons lost per H2S, which is the reactant. Now, if we look over here at oxygen, how many electrons were lost for the O2, which is our reactant? Well, the answer is 4. 4 electrons lost per O2. Now, the common answer that people want to put here is 2. Oh, wait a second. Let's fix that. That should be gained per O2 atom or O2 molecule. So the common mistake that people make is that they want to put 2 here. And that's because they wrote 2 up here. But if you look carefully, this is 2 electrons gained per O atom. We're talking about the reactant, which is O2. So if you've got 2 oxygens and each lose or gain 2 electrons, then in total, oxygen has gained 4 electrons. So we'll just make a little note here, because this is where people make mistakes. 2 electrons is incorrect. The reactant O2 has gained 4 electrons. 2 electrons per O atom for a total of 4. And here's where we have a problem, that one of our reactants has lost 6 electrons and one of our other reactants has only gained 4 electrons. So we've lost 2 electrons somewhere, and we can't do that. The number of electrons lost by a reactant has to be the same as the number of electrons gained by another reactant. So that's why we have to balance it. And the reason we have a different number is this is not a balanced equation. So step 4 is to find the simplest whole number. In other words, what I like to call this is the LCM. So what number is the smallest number that both of these numbers go into? So LCM is equal to, in this case, 12. That's step 4. Now, another way to sort of do this, if finding the lowest common multiple, LCM, is not your thing, is to multiply the two numbers 6 and 4 together to get 24, and just keep dividing it by 2 until you get to a point where you can't divide it anymore, where both of these numbers go into. So if I said 6 times 4 is 24, I divide that by 2, I get 12. Does 4 go into 12? Yes. Does 6 go into 12? Yes. And we want it to go in evenly. So if I divide 12 by 2 again to get 6, does 6 go into 6? Yes. But 4 doesn't go into 6 evenly. So our lowest common multiple is, in this case, 12. Now what we want to do is I sort of set this up. And if you sort of set this up, it's like a picture. Then the more you do this, the more you'll get into the habit of making the picture correct on something like a test. So what I do here is I draw an arrow from the two numbers like this, and I want to know 6 times what gets us to 12. Well, the answer to that is 2. And 4 times what gets us to 12? Well, the answer there is 3. Like this. Now, what we've done, and remember, the whole purpose for this question is to balance the chemical equation. Now, in the past, when you've balanced chemical equations, what you've done is you've looked at your reactants, saw that you had 2 hydrogens here, saw you had 2 hydrogens here, saw you had 1 sulfur here, saw you had 1 sulfur here, got to your oxygens, and tried to put numbers out front. We're not going to do this. What this method is going to do, when we track electrons, is it's going to give us the lowest possible numbers for our reactants. And then what you're just going to have to do is then you just got to put numbers in your products. There's none of this going back and forth like you've done in the past balancing equations. And on this page here, we already have figured out what our lowest numbers for our two reactants are, because that's what these are right over here. This here is my coefficient for H2S. And this here is my coefficient for oxygen. So now step 5, I think I'll just go to the next page here. What step 5 is to rewrite your equation. So we've got H2S plus O2 becomes 2SO2 plus, oops, let's pretend we don't see that there, becomes SO2 plus H2O. So that's just our original question. Now what we found is that the coefficient for H2S is 2. And I can't do it because I'm on the next page, but if you want to draw that 2 down to there, and the coefficient for oxygen we figured out was 3, and if you want to draw that from your page into there, we've got 3. So now what you want to do is you just want to balance, and I guess we'll call this 5A. You just want to balance, now that you've got these numbers here, you want to balance just the atoms that were involved in the oxidation reduction, which is sulfur and oxygen. So I'm not going to change these numbers, that's it. So on this side I've got 2 sulfur, which is why, let's go back here, I need to put a 2 here. So I've got 2 sulfur in my reactants, and I've got 2 sulfur in my products now. Now my reactants have 6 oxygen, and right now I only have 4 oxygen, from 2 times 2 is 4, and 1 oxygen here. So by putting a 2 right here, I now have 6 oxygen on this entire side. 4 here and 2 here. And the hydrogens, you'll notice I've got 4 hydrogens here, 4 hydrogen here. They have worked themselves out. So 5B is, in some scenarios, you're going to have to balance other atoms. And then that's what you would do next. In this case, we don't have any other atoms to balance because the H atom are balanced. And that's how we do balancing a redox reaction using the oxidation number when we have a non-acidic or non-basic solution. And so this one doesn't have any acids or bases.